Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go through section 8.2, which has to deal with the area of a surface of revolution. In order to talk about surface area, we're going to have to keep a few things in mind. First, an equation that we are going to use is the equation that we used that showed the length of a curve. So we had the length is from a to b square root of 1 plus the function, or the derivative of the function squared dx. Same thing if you also have that defined with y instead as the primary variable. So we are going to use that, so I just wanted to have that there as a reminder. Now, when we're thinking of surface area, what we want to think about is some, let's say, some function that looks like this, maybe. So it curves up, curves around like so. And what I want to think about is what happens if I were to rotate that around the x-axis and what the surface area would look like. So this shape will look somewhat like this. Something like that. That's what the shape would look like if I were to rotate that around. Now, if I'm trying to think about surface area, we are going to think about cross-sections like we would for volume, but we're going to think about cross-sections in a little bit of a different way. Instead of thinking about the cross-section as coming up from the x-axis necessarily, what we're typically going to do is think about a cross-section in terms of the cross-section of the length. So let's do that. So we have a cross-section like so. That's going to be the section that we are going to create when we think about the area or the surface area. Then when I rotate that surface around, I get that surface that rotates down around this way. And so I get kind of a strip. Okay, and so if I continue that, what I get is this kind of a strip here, which would also continue on the back side as well. So we get something like that. Not too bad of a picture if I say so myself. Now, if I were to try to roll that strip out, so if I were to cut that out and then roll it out, well, I'm not going to get necessarily a straight rectangle. I'm going to get something that's a little bit curved, more or less, when I were to roll that out, and maybe it'll actually even curve even more so. So this is kind of a harder shape to try to determine the actual area of. So we aren't just going to, well, we'll have to use something that really helps us designate what this shape is going to look like. And what we are going to work with is the surface area for the frustum of a cone. The surface area for the frustum of a cone is defined as the area times 2 pi, or the area is 2 pi times r1 plus r2, where r1 and r2 are the two radii, the base radii for the frustum, divided by 2 times s, which is your slant length. So if I think about a frustum of a cone drawn on the side, so similar to what I have here, a cone would look like this. And if I'm trying to find the surface area of the frustum, a frustum would be like this part of it. So the bottom piece. And the radius, r1 and r2, would be right here. This would be r1. And then right here, that would be r2. So r1 plus r2 divided by 2, that's actually the average radius. So it's basically going to find on average what the radius is. And then the slant length is this right here, s. So that would be the surface area. And that's what we're going to use because that's kind of what all these curves are going to look like. No matter if it's curving up or down, I could continue that, like if I were to continue a tangent line, and think about that, all of these as frustum of a cone. Now, I already said that r1 plus r2 divided by 2 is the average of the radius, so we can consider that r hat, which is typically how you represent an average. And with that in mind, we get 2 pi rs, which should look very familiar, and it should look like the same volume that we use for cylindrical shells, 2 pi rh. However, in this case, r is going to be the function itself. If I think about my figure here, the radius here is going to be defined as the function, whereas the slant length is going to be the length of that, which is 1 plus the derivative of the function squared dx. those two, the radius f of x and the slant length 1 plus the derivative of the function dx, those two multiplied should get me a formula that looks kind of familiar. I get the limits as n approaches infinity, where n is going to be how many partitions I do, so how often I cut up the arc length there, of 2 pi rs, where 2 pi, r is going to be f of x sub I, so at what point along the partition I am in the x direction, times the square root of 1 plus the derivative of the function at that point, delta x, and that gives me my integral. And therefore we have the formula for surface area is 2 pi from a to b, the function times the square root of 1 plus the derivative of the function squared dx. So really, it's the same thing as the arc length except for two things. You have a 2 pi out front and also a function multiplying the square root. If you were to generalize this, you can get the same thing for if it was defined with y, so the function of y and then the derivative of the function defined with y, or what we'll get to later on in chapter 10 with parametric, we have one of the functions gt times both the derivative of both of the functions added together. Okay, so again, we'll get to that last one more in chapter 10, but just food for thought moving forward. With these equations in mind, let's do a few examples. For the following examples, we're going to find the area of the surface of revolution generated by revolving the given curve about the indicated axis with the indicated bounds. So we have a curve, we have the bounds, and we're going to rotate around the given axis. For these, we're always going to be rotating around the x or y axis, just to make it simple. Okay, so we have y equals root x from 0 to 4 about the x-axis. So if I were to graph that, I have y equals square root of x. Square root of x looks like this, from 0 to 4. So we're taking this curve, we're rotating it around, and what we're basically finding is something similar to the surface area of a bowl, kind of, with a rounded tip here, I guess. So that's what we're going to be finding in this situation. And you can even draw the cross-section like this. So you can see what that cross-section looks like. Okay, now with this, we're going to need the function itself, which is good, but we're also going to need the derivative of that function. So we have y equals root x. So that's our function, is root x, but we also need the derivative of that. That's going to pull the 1/2 down, and then we're going to get x to the negative 1/2, so that's 1 over 2 root x. And then in the equation, what we're going to do is square that. So let's go ahead and square that right now. So the derivative squared will give me 1 over 2 squared is 4, root x squared is just x. So then, for the surface area, we have 2 pi from 0 to 4. In this case, since we're rotating around the x-axis, we're going to have the variable agree with that. So from 0 to 4, we have the function, which is root x, times the square root of 1 plus the derivative of the function squared, which we found to be 1 over 4x dx. Okay, so this will require a little bit of manipulation. We see this inside. What we're very often going to do is try to make this into one fraction. So I can change 1 into 4x over 4x. So we get 4x plus 1 all over 4x. And what we see there then is if I apply the root to the top and the bottom, I get the square root of 4x plus 1 up top. And on the bottom, I get the square root of 4, which is 2 times root x dx, which shows us that we're going to cancel out the root x. Now we could have also multiplied the root x in, but this basically does the same trick. So then now we have 2 pi from 0 to 4 of just, well, if I actually pull that 2 out, I just have pi then of the square root of 4x plus 1 dx. Okay. Nice and easy. Now, if you want, you can do a u sub. You could do u equals 4x plus 1 and define du as 4dx, so the 4 gets divided out. So you'll end up with pi over 4 times u to the 1/2, which means that it's going to increase to u, or 4x plus 1, to the 3/2. Then we're going to divide by 3/2, so we have a 2/3 out here from 0 to 4. So then pi fourths times 2/3 will be pi over 6 times what happens when I plug in these values 4 and 0. First, if I plug in 4, I get 4 times 4 is 16 plus 1. I get 17 to the 3/2. Minus, if I plug in 0, I get 1 to the 3/2, which is just 1. And that right there is good enough as the final answer. 17 to the 3/2 doesn't really simplify much, so we can just keep it as that. That would be my surface area calculation. Okay. Second example. We have x equals y to the third, 0 to 1 for y, and we're rotating around the y-axis. So we're going to keep the primary variable as y. If we were to graph this, you can think about what y equals x cubed looks like. Y equals x cubed looks like this. That's a cubic function. In this case, if we're doing x equals y cubed, it's going to be a cubic function as well. But it's going to be a cubic function that comes this way. Maybe I'll graph it in red so you can see the difference. So it's going to come towards the y-axis and then go out like that. So that's what the cubic function will look like, and it's going towards infinity and negative infinity. All right, and then from 0 to 1 for y, so basically from here to here, we're taking this function and we're rotating it around the y-axis. We get another kind of bowl shape. Now, again, we need the original function, so we have f of y is y cubed. But we're also going to need the derivative of that, and then we're going to need to square that derivative. So f prime of y is 3y squared. And then if I square that, I get 9y to the 4th. So then that'll give me the surface area as 2 pi from 0 to 1, are our bounds, of the function y cubed times the square root of 1 plus the derivative of the function squared, 9y to the 4th, dy. What we notice pretty nicely here, the inside is y to the 4th, the outside is y cubed. This is going to be a very nice u du situation. So we can say that u is 1 plus 9y to the 4th, giving us du as 9 times 4, 36, y to the 3rd, dy. So we just divide by 36, and we have our replacement. So that gives us area is 2 pi divided by 36. Integral of y cubed dy just becomes du. And on the inside, we have the square root of u du. Now, to save time, we can also find our bounds by plugging in appropriately. So u of 0. So if I plug in 0 for y, I get 1. And if I plug in 1 for y, I get 9 times 1 is 1, plus 1 is 10. So now this is going from 1 to 10. That gives us pi pi over 18 times root u, which we basically just did in the previous problem. It's going to become u to the 3 halves, and then we divide by 3 halves, which is 2/3 from 1 to 10. The 2 and the 18 will cancel to make 9, and 9 times 3 is 27, so we have pi over 27. We plug in 10, so we have 10 to the 3 halves, and then minus 1 to the 3 halves is 1. So we get another answer that's kind of like the previous one. And that's all she wrote. Okay. Those are the first two examples. These kind of show how we'll very often solve them. A lot of times they'll involve roots, which you can either multiply in, or you can cancel them out usually. Or they'll end up being a UDU situation. That's also pretty common. So let's do another one. Hey, look, we have another root. So we have y equals the square root of 9 minus y squared. I'm also noticing that should say x equals 9 minus y squared. Yeah. And that means the bottom one should say y. Okay. So x equals square root of 9 minus y squared. Otherwise, that wouldn't really make sense. All right. Looking at that, if you were to square both sides and then add the y squared over, what you basically have is x squared plus y squared equals 9. You basically have a circle here. You basically just have a circle with radius 3, more or less. But in this case, since we're talking about x equals the square root of 9 minus y squared, we're considering the positive versions of it. So we're really only considering this side of it, where x is positive, because this is a positive root. All right, we rotate that around the y-axis. What that'll give us is the sphere itself. And so what we'd be creating, if I do the cross-section in blue, what we'd be creating is a cross-section like this, rotating all the way around our sphere. All right, so we have our original function. We have f of y is root 9 minus y squared. If we take the derivative of that, by the chain rule, you can think about this as this taken to the 1/2. The chain rule would say we'd pull that 1/2 down, and that would become 9 minus y squared to the negative 1/2. And then by the chain rule, we then take the derivative of the inside as well, which is a negative 2y. Those 2's will cancel, so we just have really negative y over the square root of 9 minus y squared. And then we square that yet again. That'll give us on top y squared over 9 minus y squared. So then our surface area. 2 pi from the bounds negative 2 to 2. And we can actually just say from 0 to 2 if you want to make that easier and double it. We'll do that in a moment. The function is the square root of 9 minus y squared times the square root of 1 plus y squared over 9 minus y squared dy. Okay. Now again, I know what this picture looks like from negative 2 to 2. I can actually just double that, say 4 pi, and instead just do 0 to 2. That'll make my bounds a little bit easier to work with. But then I can multiply this square root into the other square root. And so what I'll get is a big square root of 9 minus y squared times 1 is 9 minus y squared. And then 9 minus y squared times the second term will cancel out that 9 minus y squared. And then we just have plus y squared dy. That's awesome because the y squared and that minus y squared will cancel out. We just have the square root of 9, otherwise known as 3, which we can even pull out and say 12 pi from 0 to 2 dy. probably one of the easiest integrals you've done in a long time. That'll just give us 12 pi y from 0 to 2. And if we just plug in 2, because 0 is just going to cancel out, we end up with 24 pi. Okay, not too bad. All right. One last one. Now again, this is y equals the quantity x to the 6 plus 2 over 8x squared, 1 to 3, about the x-axis. So I'm going to rewrite that one again. This means y equals x to the 6 plus 2 over 8x squared. Now to rewrite that, I could just make that into two fractions, which is going to be a little bit easier to take the derivative of. I'll say this is f of x. 8x, or x to the 6 over 8x squared will give me x to the 4th over 8. Plus 2 over 8x squared will give me 1 over 4x squared, otherwise known as x to the negative 2nd over 4. Now this might look familiar from a problem we did in the arc length section, because it is basically one of those. If we take the derivative of that, we end up getting, the 4 comes down, we get x to the 3 over 2. And then for the second one, the negative 2 comes down, and we get minus x to the negative 3rd over 2. Now what we're going to then do is square that term. Which will give us x cubed over 2 multiplied by itself. Will give you x to the 6 over 4. Then if I multiply the inside terms, x cubed times x to the minus 3rd will cancel out. Will give us a minus 1/4. And then we'll get another one we multiply the other way. So we'll actually get 2 minus 1/4, which overall is a minus 1/2. And then we have the last term squared, which is plus x to the negative 3rd by itself, or multiplied by itself, is x to the negative 6th, over 2 times 2 is 4. And that's our squared term. Okay. Now, if we put that in for our surface area, we get 2 pi from 1 to 3. The trouble is that we're going to have this term on the outside as well. We're going to have x to the 4th over 8 plus x to the negative 2nd over 4. But then we have the square root of 1 plus x to the 6 over 4 minus 1/2 plus x to the negative 6 over 4 dx. That inside we've done before. X to the 4th over 8 plus x to the negative 2nd over 4. This inside, the minus 1/2 and the 1 will combine, and we'll get x to the 6 over 4 plus 1/2 plus x to the negative 6 over 4 dx. And if we yet again notice, the amount that's inside the square root looks almost like what I started with in it. This just has a minus 1/2, and that's because it was a minus value squared. Now that this is a plus 1/2, this is going to be the square root of x cubed over 2 plus x to the negative cubed over 2 quantity squared dx. This is going to cancel out appropriately. So we get 2 pi from 1 to 3, x to the 4th over 8 plus x to the negative 2nd over 4 times x cubed over 2 plus x to the negative cubed over 2 dx. Now this is just a polynomial. It's a longer polynomial, but one we can do regardless. Okay, the first terms multiplied, so just foiling out here. X to the 4th times x to the 3rd is x to the 7th over 8 times 2 is 16. Then x to the fourth over 8 times the last term will give us x over 8 times 2 is 16. Then x to the negative second times x cubed will give us another x, but this one over 8. And then the last terms multiplied will give us plus x to the negative fifth over 8 dx. All right, we can combine a little bit here to get x to the seventh over 16, plus that's going to be 2x over 16, so that's overall 3x over 16, plus x to the negative fifth over 8 dx. And now we can solve that. That will increase that x to an 8. And then we're going to have 16 times 8 on the bottom, which is 64 times 2, so that's 132. No, 128. Okay. Then plus 3x, which is going to become 3x squared, and then we divide by 2, which is going to make that a 32. And then this is going to increase to an x to the negative fourth. That minus is going to come down, and then we divide by 4, so 4 times 8 is 32 again. We take this from 1 to 3. All right. At this point, it's all just about plugging in those values. So you get 3 to the 8th, which is 3 to the 6th is 729. 3 to the 8th is 6561. Yeah. 6561 over 128. Plus 3 times 9 is 27 over 32. Minus 3 to the negative fourth would actually pull it down. And that's basically 9 times 9, so that's 81. So you have 1 over 81 times 32. That one I don't know off the top of my head. Minus all these with a 1 in it, so 1 over 128 plus 3 over 32 minus 1 over 32. And then whatever this expression evaluates out to as a decimal, or if you can make a simplified fraction. It's possible, but with that 81 times 32 there, that really makes it gross to do, so I'd probably just get this as a decimal. All right, but whatever that comes out to be would be your final answer there. At that point, it's just typing in the calculator. All right, so those are some examples of dealing with surface area and some examples that you could end up seeing. This last one being probably the more complex variety, but we've done something like this with arc length before, so hopefully not too alien. If you have any questions, feel free to put those in the comments below or ask your instructor. That said, I hope you have a nice day.